So in this video lecture, we're going to look at some nervous system and muscular system functioning, particularly that stuff that is important to remember from your Anatomy and Physiology 1 class that would pertain to cardiovascular system, particularly heart functioning. So things like action potentials, how a skeletal muscle contracts, so we can relate it to cardiac muscle contraction, and then what's called muscle tetanus. So let's start with the action potentials. Now, we're going to assume we get a threshold stimulus. We're going to deal with graded potentials versus action potentials. Let's just say we get a stimulus big enough to cause an action potential. So we want to look at the steps of what happens in an action potential. So let's first start with the resting membrane. Before we have any kind of stimulus causing an action potential, what's it look like? Well, remember, sodium's concentrated outside, potassium's concentrated inside. Notice that these sodium channels are closed, that their activation gates, which are these little pinches here, are closed. These inactivation gates, what look like little caps, are open, so therefore we can activate this guy since the inactivation gates are open. Crazy system of naming things, but unfortunately that's what they did. And then notice also the potassium channels are closed as well. Notice they only have activation gates. They don't have some inactivation thing going on. So this is our setup when it's at rest. Both channels are closed, sodium and potassium. Now there's a few leaky potassium channels. Think of this as your dripping kitchen sink that just won't fix itself. I mean, it's just there's a little sodium leaking out. That's okay. It doesn't really matter. It doesn't change or affect anything we're looking at. So now we hit it with a stimulus. When you hit it with a stimulus, notice we start getting depolarization. That's here in 2 and 3, depolarization. Now in depolarization, what happens is those activation gates start to open up, especially when you start out low, maybe just a couple open up. And that causes sodium to rush in. So we have an influx of sodium, adding positive to the inside, making the inside less negative or more positive. Now, as we build up and go up in depolarization, that becomes a positive feedback system, opening up more of those activation gates, and therefore more sodium rushes in. By the time we hit the peak here, all those sodium channels are open, and as much sodium as we can was moving in. That triggers potassium channels to begin to open and for the inactivation gates to close. So now we're up here. Notice if the inactivation gates are closed, we can't have any more sodium moving in. With the potassium gates now open, potassium rushes out. That means now we're removing positives from the inside, making the inside more negative or less positive, which means we get repolarization. And we get a little hyperpolarization extended here. That's okay. It just happens because those potassium channels are kind of sluggish in their ability to close to get back to resting membrane potential. And that's what we end up over here. Notice we're back to normal here. We've got all the channels closed and the inactivation gates are open. So basically we're back to where we were at the beginning. So a couple things to note on this one is that, again, sodium influx is the cause of depolarization, potassium efflux is the cause of repolarization, and during part of that repolarization, our sodium channels are inactivated. They can't, and no sodium can move in, even if notice the activation gate here is open still, but since it's inactivated, it doesn't matter. It's inactivated. You can't do anything about opening it up. So that brings us to then the refractory period. Now the refractory period kind of is a recovery period, or actually it's divided into think of an absolute refractory period or a relative refractory period. The absolute refractory period here is in this kind of salmon color. This is the time in which there's no stimulus, I don't care how big it is, can cause another action potential. So there's absolutely no way, no how you're going to get another action potential generated during this period in time, which in part of it makes sense. If you've got depolarization going on anyway, you're in the middle of an action potential. But even during repolarization, if I hit it, say with a stimulus right here, I can't get another action potential generated. Okay, because I'm in what's called the absolute refractory period. there's enough of those sodium channels that are inactivated that if it gets hit by another stimulus, those sodium channels are inactive. They can't be opened up. And so we have to get past this absolute refractory period down here where enough of the sodium channels are now, there's inactivation gates are open, but the activation gates are closed, so we're back like this scenario. So during this time, we have too many, whoops, I went the wrong way. We have too many of the inactivation gates closed for us to generate another action potential. During this time, in the relative refractory period, we have enough inactivation gates open and the activation gates closed that if I hit it with another stimulus, I could generate an action potential. So basically, remember, if the inactivation gate stuff doesn't make a lot of sense, it's okay. It's not really absolutely necessary to get that down. What you do, if you want to take it by faith, that's fine. Basically, absolute refractory period, absolutely no way, no how I can get another stimulus, cause an action potential. Relative refractory period, a stronger than normal threshold stimulus could generate an action potential. Okay? Now let's look at muscle contraction. In muscle contraction, we start out first, of course, with releasing acetylcholine from the neuron and the neuromuscular junction. The acetylcholine binds to receptors. That eventually leads to an action potential to travel across the surface of the muscle fiber and then even down the T-tubules. Now, when that action potential is generated, a bunch of stuff's going to happen. Number 3 here is just pointing to the fact that acetylcholinesterase is going to remove the acetylcholine from the cleft, and therefore we don't keep generating action potentials. We'll just, for example, just think we generated one action potential that's traveling along the surface of the muscle fiber. In response to this action potential, sarcoplasmic reticulum is going to release calcium. Calcium then goes to troponin, which is right here in the red, and binds with it. Now the blue is tropomyosin. Now when calcium binds to troponin, it causes tropomyosin to move out of the way of these little binding sites in the dark green that are on the actin beads. These binding sites is where myosin grabs a hold of the actin to form cross bridges. So with calcium present, then the binding sites are exposed, myosin grabs a hold of the actin, that's a cross bridge, it swings its head in, and you get a muscle contraction. As long as calcium's present, the muscle can contract. The more calcium I have in there, the more binding sites that are available, the more myosin heads can grab a hold of it, the more cross bridges form, and the stronger the contraction. So if I get release of calcium, I get lots of binding sites exposed, I get cross bridges form, I get muscle contraction. Now as soon as the calcium's released, it's going to get started to get pumped back in, and the calcium gets pumped back into the sarcoplasmic reticulum. If I pump all that calcium back into the sarcoplasmic reticulum, that means there's no calcium now on the troponin, which means the tropomyosin moves back, covering the binding sites. Myosin can't form cross bridges anymore, so the muscle is going to relax. Okay? Now that comes, if we put the two together, let's think it that way, we have what's called a muscle twitch. So here we hit with an action potential. Now that action potential causes release of calcium. Calcium means we can form cross bridges. Cross bridges form, we get muscle contraction, so the force of the contraction increases. And then calcium gets pumped back into the sarcoplasmic reticulum, so I can't form cross bridges, so the muscle relaxes. That's a muscle twitch. Now if I hit that muscle with consecutive action potentials, so I hit it here with one, I get the muscle contracts a little bit, so calcium's released. Now the muscle starts to relax a little bit, so some of the calcium goes back in the sarcoplasmic reticulum, but I still have some calcium in the cytoplasm. And I hit it with another action potential. When I hit it with another action potential, I'm going to release even more calcium from the sarcoplasmic reticulum. So that's adding additional calcium into that cytoplasm. I already had some calcium there because we didn't pump it all back. since the muscle didn't completely relax, which means now I've got more calcium in the cytoplasm, meaning more cross bridges, even a stronger contraction. And then eventually all that calcium is pumped back in and I get a muscle to relax. Now, if I keep going with consecutive stimulus one after another, I get this kind of stepwise process of increasing muscle contraction, because what I have is every time the muscle begins to relax, I hit it with a contraction, I release more calcium, which means I build up calcium in the cytoplasm. As I build up calcium, I can form even more cross bridges, which means I get even a stronger contraction, and it keeps moving and getting increase in the force of the contraction. Okay? So again, it's all related to the idea that the more calcium that's in that cytoplasm, the more cross bridges that form, the stronger the muscle contraction. This is either called wave summation or what's called unfused or incomplete tetanus. Now, if I make these action potentials come in really, really close together, and so close that the muscle never has a chance to relax, I'm just going to build up calcium and I'm going to hit a maximum force of contraction. That is, I've got so much calcium in there, I've formed every possible cross bridge I can make. Every cross bridge is formed, I get maximum amount of contraction, and I maintain that contraction. Notice there's no relaxation at all. I'm going to maintain that contraction as long as I keep having stimuli hitting it. So this is basically why I can hold, say, a book up in my arms. If I had my arm extended out, I can hold a book up, because think of the biceps basically as I've hitting it with action potential one after another to keep that bicep contracted and therefore hold that book up on my arms. Okay? And that's going to come important again with cardiac muscle, because we don't want tetanus in our cardiac muscle. If the cardiac muscle contracted and stayed contracted, it wouldn't be a very effective pump. So we're going to see how the cardiac muscle prevents tetanus, and that's going to have to do with the shape of the action potential and therefore the length of that refractory period. Now, the last thing I want to mention is this idea of muscle length tension relationship. That is, how many cross bridges can you form? Let's assume there's tons of calcium. We're not going to worry about calcium levels. We're thinking about the length or the relationship of the myosin heads with the actin. So it's basically, again, I kind of refer to this a lot, but a Goldilocks principle. I need an optimal length, kind of the middle length. That is, at this middle length, I've got maximum overlap of myosin heads with the actin filaments. Okay? And that way I can form tons of cross bridges. If I can get lots and lots of cross bridges, I can have maximum contraction. Okay, so I have maximum tension or contraction. If I shorten the length, that is, I squeeze, like, because I think of just squeezing both ends of the muscles and kind of squeezing them in a little bit, then notice here I've squeezed it in so much that those actin filaments are overlapping. Since they're overlapping, there's no place to go. I can't contract the muscle as effectively, so I get less muscle contraction. If I stretch the muscle out, now notice some of the myosin heads aren't even touching any of the actin. So they can't form cross bridges. There's no actin above them to bind with. So you're going to get less and less contraction. So again, if the length of the muscle is too long, I've overstretched it, it's too long, I get crappy muscle contraction. If it's too little or too tight, close together, or squeezed together, then I get crappy contraction. I want this optimal length. That is, in the middle, I've got perfect overlap of myosin with actin, so I get maximum contraction. Now, our skeletal muscles are designed to be always at this optimal length. That is, the length of the tendons and the way the muscle is stretched across our bones maximizes this or optimizes this length tension relationship. So all our skeletal muscles are in here. Okay. Now we'll see cardiac muscle is at rest is more over here. If we slightly stretch it a little bit, it becomes optimized, and that's what's going to allow us to have even bigger muscle contractions. So we'll look at that as well when we do cardiac muscle. So keep this one in mind as well. A little bit of stretch is going to increase muscle contraction strength. Okay, so that's going to end where we're at with these review stuff. So again, keep looking and going over this, because again, we'll come back to it and see how it relates to cardiac muscle.